Welcome back to Mr. Vaughn's classroom, where math is made easy. Today we're looking at Unit 7, Quadratic Equations, Lesson 6, Rewriting Quadratic Expressions in Factored Form. This will be part 1 in a series of lessons. The learning goal today is to write expressions in factored form. If you think back to Unit 6, several times we took the factored form and we used the distributive property to rewrite them in standard form. Now, as a way of solving these quadratic expressions, we are going to do the opposite. Now we're going to start learning how to take the standard form and rewrite them into factored form so that we can solve them that way. We have 3 learning targets in this lesson. At the end of the lesson, we'll come back, we'll review these, and we'll make sure that you've learned everything that you needed to in this lesson. Learning target number 1 says I can explain how the numbers in a quadratic expression in factored form relate to the numbers in an equivalent expression in standard form. So basically understanding that if I'm looking at factored form, my x terms are going to multiply together to give me my ax squared term in standard form. My constant terms are going to multiply together to give me my c term in standard form. And my x terms and my constants are going to multiply together and then add or subtract together in order to give me my bx term in standard form. Learning target number 2. When given quadratic expressions in factored form, I can rewrite them in standard form. This one, hopefully, you are already comfortable doing. We did this several times in Unit 6 simply by using the distributive property, or we also showed the area model. Either one of those will work to go from factored form to standard form. And learning target number 3, when given quadratic expressions in the form of x squared plus bx plus c, meaning standard form, I can rewrite them in factored form. So you need to be able to understand how to break that standard form into factors that, if you were to multiply those factors together, would go back to standard form. So as we go through the practice problems today, these are the 3 learning targets. Keep these in mind so that you're picking up when we're covering these. And at the end of the lesson, we'll come back and we'll review them again. Our first glossary term for this lesson is coefficient. In an algebraic expression, the coefficient of a variable is the constant the variable is multiplied by. If the variable appears by itself, then it is regarded as being multiplied by 1, and the coefficient is 1. We've seen this a lot. The reason that it is understood to be 1 is because multiplying by 1 doesn't change anything. So therefore, we don't usually show the 1. We just understand that it's there. So they give us a couple of examples here. The coefficient of x in the expression 3x plus 2 is 3, because that is the constant that the variable is being multiplied by. The coefficient of p in the expression 5 plus p is 1. So again, if you see just a variable without a number being multiplied by it, then it's understood that you're multiplying that variable by 1, because you're saying you only have one of those variables. Our next glossary term, constant term. In an expression like 5x plus 2, the number 2 is called the constant term because it doesn't change when x changes. So they give us a couple of examples here. In the expression 5x minus 8, the constant term is negative 8 because we think of the expression as 5x plus negative 8. In the expression 12x minus 4, the constant term is negative 4. So they're just trying to make you understand the difference between the term coefficient and constant. A coefficient is when you have a number that is being multiplied by a variable. A constant is when you have a number all alone. Our next glossary term is linear term. The linear term in a quadratic expression in standard form, ax squared plus bx plus c, where a, b, and c are constants, is the term bx. If the expression is not in standard form, it may need to be written in standard form first. So a linear term essentially is when you have x with no exponent or x to the power of 1. This is when we refer to something as being the linear term. So the constant term is the number that's by itself. It doesn't have a variable that it's being multiplied by. We call that the c term. The linear term is where you have x with no exponent or also x to the power of 1. This is the linear term. So in standard form, it's our bx term. And then our last glossary term for this lesson is zero product property. The zero product property says that if the product of two numbers is 0, then one of the numbers must be 0. And we've talked about this a lot in Unit 6, where we were saying if you're going to multiply any two things together, but you're telling me that the answer is 0, then I know that one of those things I'm multiplying together must be 0, because that's the only possible way to get 0 for the answer. So now we can move into the practice problems. Remember that if you have any questions, please always feel free to leave a comment, and I will get back to you with any help, any answers that I can provide you. So now we can begin on the practice problems for Unit 7, Lesson 6. And what we're trying to do in this first problem is get you used to understanding the basic part of the math that is going to be required in order to start factoring these standard form equations into factored form. So on this first problem, it tells us to find two numbers that satisfy the requirements. And their note is that if we get stuck, we can try listing all the factors of the first number. So number 1 wants us to find two numbers that multiply to equal 17, but if you add them, they equal 18. Well, number one's pretty easy. There's only two numbers that multiply to equal 17. It's a prime number. And this is going to be 1 and 17. 1 times 17 equals 17, and 1 plus 17 equals 18. So the first problem is pretty straightforward and easy, just to get you used to the idea of what we're going to do here. Now, number two is a little bit more challenging. You're trying to think of two numbers that if you multiply them together, they're going to equal 20. And if you add them together, they're going to be 9. So we've got 1 times 20, but if I add those, that's going to be 21. So it can't be 1 and 20. Then we could have 2 and 10. They multiply to 20. But if I try to add them together, I get 12, not 9. 3 does not multiply by anything to make 20 exactly. And then we have 4 times 5, which is 20. And then 4 plus 5 equals 9. So for number 2, the numbers we're looking for are 4 and 5. Because 4 times 5 equals 20, and 4 plus 5 equals 9. Number 3. This time we want two numbers that if we multiply them are going to be 11, and if we add them, they're going to be negative 12. So this one is a lot like number 1, but now we have this new twist where when we add them, they're going to be a negative. So if I think about multiplying numbers to 11, I get 1 and 11 because 11's a prime number. But if I add 1 and 11, I get 12. So the twist here is that not only do you get a positive number when you multiply two positive numbers together, but you also get a positive number if you multiply two negative numbers together. So it turns out what we're looking for would be 1 or negative 1 and negative 11. Now, if I were to say negative 1 times negative 11, the negative times the negative is positive, and 1 times 11 is 11, which is what we were looking for. And now, if I were to say negative 1 plus negative 11, then I'm starting at negative 1, and I'm getting even more negative by 11. And so this would give me the negative 12 that I'm looking for. So they're trying to get you used to this idea of understanding that not only could your answers be positive, but your answers could be negative. And then multiplying those negatives together could create you a positive, but adding those negatives together could still leave you with a negative. And number 4, we want two numbers that multiply to 36, but add to 20. So I need two numbers that multiply together to 36, but they're 20 apart. So if I start thinking about it, 1 and 36, they're only 35 apart. 2 and 18. Well, I could make 2 and 18 come together to be 20, but a positive 2 and a positive 18 aren't going to give me negative 20. So I want a negative 2 and a negative 18. Now, multiply these two negatives together. Negative times a negative is a positive, and 2 times 18 is 36. So I'm good there. But then if I go ahead and I add these negatives together, then a negative 2 plus another negative 18 is going to take me to a negative 20. So this is how we would solve the first practice problem. They're really just getting you used to this idea of thinking about numbers that are going to multiply together to get you one thing, but they're going to add together to get you something else. And they're trying to get you used to this idea of not only do positive numbers multiply together to get you a positive answer, but negative numbers being multiplied together also get you a positive answer. So you're really going to have to start getting used to understanding your factors, understanding what numbers multiply together to create certain numbers, but then also thinking, how do those numbers combine together when I add or subtract them? So if you have any questions about this practice problem, remember, you can always leave a comment below, and I'll get back to you with any help that I can offer. In practice problem 2, they want us to take these factored form quadratic expressions and show that they are equivalent to the standard form. And the method that they're using might look new, but it's really just the area model that we used back in Unit 6. Only instead of drawing the interior squares and then writing the factors on the outside, they've written the factors in squares and then left the interior kind of open. So all we're really doing here is that we're going to multiply what is at the top of each column with what's on the left side of each row, and we're going to write their answers where they combine. So we have this x times this x, so we're going to get x squared. And over here on the right, we also have an x times an x, so we have an x squared. Next, we can come over here and we say that we have a 2 and we have this x, so that's going to give us 2x. And then over here on the right, we've got this negative 10 at the top, and we've got this x on the left. So when we multiply them together, we're going to have negative 10x. Now we go to the bottom left, or I guess middle bottom. We've got this x at the top, and we're going to bring it down, and we're going to multiply by this 4 on the left, and that's going to give us a 4x. And then we'll do the same thing over here on the right. We're going to bring this x down, and we're going to multiply it by this negative 3, and that's going to give us a negative 3x. And then finally, we're going to take this 2, bring it down, and multiply it by this 4, and 2 times 4 is 8. And then on the right side, we're going to bring this 10 down, and we're going to multiply it by this negative 3 on the left, and a negative times a negative is a positive, and 10 times 3 is 30. So once we have our entire table filled out, we're simply going to add all of these answers together. So on the left side, we've got x squared plus 2x plus 4x plus 8. We can combine the x terms, and if we do that, we bring down the x squared. 2x plus 4x becomes 6x, and then we bring down the 8, and we see that the answer we get is exactly the same as the standard form that they wanted us to prove it equaled. So that this shows the factored form and the standard form are equivalent. Now on the right side, we'll do the same thing. We've got this x squared in red minus 10x in blue minus 3x in orange and plus 30 in green. We're going to combine the x terms, so we'll bring down the x squared. Negative 10x minus 3x is minus 13x, and then we bring down the plus 30. And what you'll notice is that the answer we get exactly matches the standard form they wanted us to prove was equivalent. So we've talked about being able to just use the distributive property, or FOIL, and we've talked about this diagram method as well. They both work. They'll both get you the right answers. They'll both allow you to switch from factored form to standard form. So it really just depends on which one you prefer, which one makes more sense to you, which one is easier to you. Pick that method and stick with it. And if you have any questions about any part of this practice problem, remember, you can always leave a comment and I'll get back to you with any help or answers that I can provide. Practice problem number 3 wants us to select all expressions that are equivalent to x minus 5. Now, something I want to point out here. We're taught a lot that the order of multiplication doesn't matter because 2 times 3 is also the same as 3 times 2. And we're taught that the order of addition doesn't matter because 2 plus 3 and 3 plus 2 are the same. But a lot of times we are taught that the order of subtraction matters because 2 minus 3 is not the same thing as 3 minus 2. And I kind of want to put this a different way. All right, it's not the order that matters, it's the signs that matter. So I want to put a note here that says order doesn't matter if the signs stay the same. because we're going to see this a lot moving forward. Okay. So if I want to know which ones are equivalent to x minus 5, then what I need to understand is that I have a positive x and I have a negative 5. So as long as these stay the same, then they are going to be equivalent. So if I look at choice A, I see that I have a positive x and I'm adding a negative 5. Well, if I add a negative, then that is still the same thing as minus 5. And that is because I end up with the positive x and the negative 5 that I wanted. So A is equivalent. Now, if I look at B, I do have my positive x, so I'm good there. But then I have minus a negative 5. And if I subtract a negative, it becomes positive. So now I'm going to have a positive 5, and that's not what I have up at the top. So B is not equivalent. If I look at C, what they've done here is they have swapped the order. Instead of x minus 5, we have minus 5 plus x. But if you break it down into its components, we have the positive x, we have the negative 5, and that is all we really cared about. We don't really care about the order. We care that the components have the same signs. So C is equivalent. So now choice D. Again, the order is opposite, but what you notice is now we have a negative x. And we did not have a negative x in the example. We had a positive x. We still have our negative 5, which is what we want, but because D has a negative x, these are not equivalent. Choice E. They have swapped the order and left the minus sign in the middle. But if you break it down into the components, what we have is a negative x and a positive 5. This is actually the exact opposite of what we had at the top. So these are not equivalent. Now we can look at F. We have the negative 5, and that's what we want. Then we have a minus negative x. And when you subtract a negative, you turn it positive. So we actually do have the positive x that we wanted. So F is equivalent. And our final option, G, we have 5 plus x. We have that positive x that we wanted, but we also have a positive 5. And we don't want that positive 5. We wanted it to be negative. So G is not equivalent to the one at the top. So if we look at all of these answer choices, the only ones that are equivalent to x minus 5 are choice A, x plus negative 5, choice C, negative 5 plus x, and choice F, negative 5 minus negative x. If you have any questions about this practice problem or how I've explained it, please leave a comment below and I'll get back to you with any help that I can offer. Practice problem number 4 says here are pairs of equivalent expressions, one in standard form on the left and the other in factored form on the right. And what they want us to do is find the missing numbers. Now, 1 is actually the more complex problem. So I'm going to show you how to do numbers 2, 3, and 4, and then we'll come back to number 1. In number 2, 3, and 4, what you'll notice is that they have given us the complete standard form on the left, and on the right, we're just missing that last constant term in the factored form. So what you need to start piecing together is that the x terms multiply to give you x squared term. X terms multiply with constants to give you bx terms, and constants multiply to give you C term. So what we can do with 2, 3, and 4 is we can take the C term and divide it by the number that we know in the factored form. And that will tell us the number that's missing. Because if we multiplied the two constants from the factored form, they would give us the C term. So for number 2, I'm going to say 32 divided by 4 equals 8. So this missing square is 8, and we know that because 4 times 8 would multiply together to give us the 32. Now we can look at number 3. I'm going to take that C term, 35, and I'm going to divide it by the constant that I do know in the factored form, which is negative 5. Now, if I divide a positive number by a negative number, then I'm going to get a negative number. And if I divide 35 by 5, I get 7. So my missing box here is negative 7. And I can check myself because if I were to use the distributive property here, negative 5 times negative 7, negative times a negative gives me a positive, and 5 times 7 gives me 35. So I know number 3 is correct. And on number 4, same thing. I'm going to take my C term, which is 20, and I'm going to divide it by the constant in the factored form that I do know, which is negative 4. Again, if I divide a positive number by a negative number, I get a negative number. And if I divide 20 by 4, I get 5. So my empty box here should be negative 5. And if I want to check myself, negative times a negative gives me a positive, and 4 times 5 gives me 20. So I know that number 4 is correct. Now I'm going to come back up here to number 1. We said down here in the notes that the x terms are going to multiply with the constants to get us the bx. And we said that the constants are going to multiply together to give us the c term. So first I'm going to look for the c term. That's going to be negative 9 times negative 3. A negative times a negative is a positive, and 9 times 3 is 27. So my c term is going to be 27. The last thing I need to do is find my bx term. So I'm going to multiply x times negative 3 and that's going to give me negative 3x. Then I'm going to multiply negative 9 times x. And that's going to give me negative 9x. Now I'm going to combine these x terms, and negative 3x minus 9x gives me negative 12x. So what I'm missing here is negative 12. So if you have any questions about how to use the factored form to find the standard form, or how to use the standard form to find the factored form, remember you can always leave a comment below and I'll get back to you with any help that I can offer. Practice problem number 5 is our last practice problem in Unit 7, Lesson 6. This problem is actually going back and checking your understanding of functions from Unit 4 to make sure that you have this knowledge to be able to solve problems here in Unit 7. Lynn charges $5.50 per hour to babysit. The amount of money earned in dollars is a function of the number of hours that she babysits. Which of the following inputs is impossible for this function? So we've got to remember the key words that help us solve a problem like this. Is a function of. Every time you read these words, whatever comes before them, amount of money earned in dollars, is your output. Whatever comes after these words, number of hours that she babysits, that is your input. And so they're wanting to know which input is impossible. So which number could not be a number of hours that she babysits? So we have 2, she could babysit for 2 hours. 5, she could babysit for 5 hours. 8, she could babysit for 8 hours, maybe watching a child while the parent is working. But the only one that doesn't make sense is -1. You can't babysit for -hours. And that's what this one would be saying. This would be saying she's babysitting for -1 hours. So we know that the input for this problem needs to be 0 or greater. And even 0 is questionable whether it makes sense, because if she doesn't babysit, she doesn't make any money. So A is the only one here that doesn't make sense, because the input is referring to the number of hours that she babysits. So that cannot be negative. Now, before we're finished with this lesson, let's go back, review the learning targets, and ensure that you learned everything you needed to before we move forward to the next lesson. Reviewing our learning targets for this lesson, number 1 says that you can explain how the numbers in a quadratic expression in factored form relate to the numbers in an equivalent expression in standard form. So what they're hoping you understand here is that by multiplying the x terms together, it will create your ax term in standard form. By multiplying one x term with one constant term, it will create your bx terms, which you can combine together. And by multiplying your constant terms together, it will create your c term in standard form. Learning target number 2 says that when given a quadratic expression in factored form, you can rewrite them in standard form. We know that we can do this using the distributive property, or FOIL, and you can use the area diagram in order to do this. Both will give you the same answer, so whichever one makes more sense to you, use that method. And learning target number 3 says that when given quadratic expressions in standard form, x squared plus bx plus c, you can rewrite them in factored form. And we started looking at how we might do this. We started looking at understanding how numbers can be multiplied together to get one result, but added or subtracted from each other to get another result. And as we move forward, we're going to look at how to figure out what those numbers are going to be. So if you found this video helpful, on the screen somewhere you should see a video that YouTube believes will also be helpful to you. If you could give this video a thumbs up, hit the subscribe button and engage with a comment below. And I look forward to seeing you in the next lesson.